Okay, we are live.
Okay, good morning, everyone. Welcome to the sadly last day of this conference. So we're very happy to have Fakher telling us about negative sign-free realistic and toy model quantum Monte Carlo calculations of correlated Dirac systems. Please take it away.
Thank you very much. So thank you guys for the organization of this conference. I mean, all the talks I could hear were absolutely marvelous. So I hope to keep the level up. So I'm a solid state physicist, and we do Monte Carlo simulations of, sort of like, hopefully things which we find and maybe hope you find interesting. So here's the importantly, these are fermionic systems, right? So we try to concentrate on problems where fermions are really play a dominant role. So here's the outline of the talk. So I'll spend some time introducing this fermion Monte Carlo, and then I have a set of subjects, which is one which I call fermion superconductivity, and it's a realization of a model actually which has a deconfined quantum critical point, but which is differently from the JQ model. Some of you I know the JQ model, which Anders introduced. As opposed to the JQ model, it has no monopoles. So it's a monopole-free realization of a deconfined quantum critical point. And then, so this will be one part. The next part is then, if you follow, the field theory for DQCPs, then you will come to a Lagrangian, basically of a two plus one dimensional nonlinear sigma model with an SO5, basically symmetric nonlinear sigma model with a Wessumino-Witten term. And this could be, I mean, maybe we don't believe it now anymore because of conformal bootstrap bounds, but it could be in principle that the DQCP could be very close to this critical point, and then to this model. And then the question is, can we do some simulations of this field theory? And the answer is yes. We can do sign-free simulations of this field theory and show that, well, maybe that it does support a CFT, an SO5 CFT. So I'll show you this. Then I won't talk about Kondo breakdown transitions because I think I won't have so much time. I mean, even if you have 2 hours, 2 hours is also finite. So Kondo breakdown transitions, I won't do that. And then if I have time, I hope I will have time, some very recent work on exotic quantum criticality in Dirac systems. So this is rather new. This is a transition in Dirac systems where you only partially gap out some of the Dirac cones. Explicitly, it is an SO3 model, and 2 out of 3 Dirac cones acquire a gap. So it's like a sort of Costes-Neveu type transition, but where you don't open a full gap. And then the model we came up with to study this is actually has another phase transition, which is even more interesting, maybe. It seems to be some type of continuous transition between a metallic state, a metal and insulator, and they have 2 different symmetries. So it would be something like if we guess a bit, it would be maybe something like a metallic deconfined quantum critical point, but that is very speculative. Okay, so you guys should, stop me at any point if something is not clear, if I'm, et cetera, et cetera. So before I start, these are the people who work in Würzburg, so many thanks to them because they do most of the work and they keep me interested in stuff, right? So thank you to all of them. And I will, a lot of the work I will show you basically is based on their work and collaborations with them and other people. Good. So let me start with fermion Monte Carlo. We heard a very nice talk yesterday by Uwe, and Uwe said very clearly, and he's correct, as usual, that what we can do with Monte Carlo very well is thermodynamics. So thermodynamic equilibrium, and that's what we will do. If you try to, as he said yesterday, if you try to go to real time, then you have real problems or sign problems. I'll talk about this, not for real time, but sign problems which also occur along the imaginary time. So the idea is the following. It's in principle simple. You start with a partition function of your favorite many-body problem, and then you'll split it up. Just do a Hubbard-Swiatkowicz transformation, or you write it in this way, right? And you find a way to write it as an integral over a field, which is space and time dependent. And then for each of these configurations of the field, then you have an action. And the point is that the action, you should be able to compute the value of this action in polynomial time for a given field, right? So if you're able to do that, to compute this in polynomial time, then you can do this high-dimensional integration with Monte Carlo methods. And then, if the action is real, this is a positive object, then you can do some importance sampling, and you can, in principle, have something rather amazing. Is you start with an exponential problem because this Hilbert space is exponentially large in the number of degrees of freedom, and then you reduce it somehow to something which becomes polynomial. That works in some cases, and that is absolutely remarkable. So let me give you some explicit examples of this for models of graphene, right? So this would really be the model which would describe graphene, or graphene is a discretization, if you want, is a lattice regularization of QED3 in a certain sense, right? So the model I have in mind would be tight binding electrons on a honeycomb lattice. So that would be a discretization of the Dirac Hamiltonian. And then this would be long-range Coulomb repulsion, so 1 over R in real space. And this N of I is basically the density, and this is the density measured away from half filling. So you know that if you take graphene, freestanding graphene, then it's a half-filled it's a half-filled state. You just recount the electrons, then the chemical potential is exactly at is pinned, if you want, at the Dirac cone. So how do we put that on the computer? Well, the first thing is to do a Trotter decomposition. So this is it. So we have a small imaginary time, delta tau. So L tau times delta tau is equal to the inverse temperature. And contrary to what Uwe said yesterday, we will keep delta tau finite, right? So this in these fermion Monte Carlo, there is no systematic and robust way of doing continuous time, as Uwe was telling yesterday, for those spin systems. So, so we will keep delta tau constant and hope that we will be able to take delta tau small enough so that we will not change the universal properties of the system. Good. So that's set. Then once we've separated the kinetic energy and the V term, then we essentially carry out a Gaussian integration, right, to split this two-body term here as a one-body term, N of I minus 1, which couples to the field. What's important, it couples with an imaginary, with an I here, right? And if you take care to integrate out, do a Gaussian integration over those fields phi, then you will in fact recover V, this term here. So that's just a Gaussian integration. Now, this works only and only if V is positive semi-definite, otherwise the Gaussian integration just blows up. Okay, so you have already one constraint, that V has to be positive definite, and essentially this gives you some restrictions on the type of repulsions you can look at, right? So for example, you cannot put a very, very big nearest neighbor interaction and a zero on-site interaction. That will give you something which is negative definite. We actually cannot simulate. So these are constraints which come in when you do the formulation. Now, at this point, the fermions are all bilinear. H0 is a kinetic energy, so everything is bilinear. So you can integrate out the fermions, and you will get a determinant. Here you get a determinant to the squared, because the fields couple symmetrically to the spin up and the spin down. Okay, so this is a method which has been introduced a long time ago from the high energy community, was used by Maxime, was used by us, and many other people, right, to simulate really graphene with long range Coulomb repulsion. Good. So one important thing is, what about the sign problem? So let me take a bit of time to talk about this because it's important. And we would like to show that the trace of this, or basically the fermion determinant, is positive. And to do this, there's been a lot of symmetry arguments to show this. And here is the easiest possible. Let's assume that we have an anti-unitary operator. So that's unitary times the complex conjugation. Okay, so unitary here. And that t squares to minus 1. And that this u, if you want, so the u is only this operator here. This u commutes with t, right, etc. So that essentially means that there is a time reversal symmetry. Now, if you have a time reversal symmetry, right, for spin 1/2 systems, then you know that if I have an eigenvalue of u, right, eigenvector of u with lambda as eigenvector, then lambda bar is also an eigenvalue, and the eigenvector is t times mu. And because t squared is equal to minus 1, then you know that these two eigenvectors, T mu and U, are orthogonal to each other. So essentially, you have to count them twice, right? They're orthogonal. So what that means is that all the eigenvalues of this determinant M, basically they come in complex conjugate pairs, and you're safe. You have no sign problem, right? So this is the easiest possible way of showing the absence of sign problem. You have to be a bit careful when you do the proof that T applied on the vacuum should be also the vacuum. So there are some constraints. Essentially, that means that you also need another symmetry, which you need a U1 symmetry, that T conserves the particle number. Okay. So how do I apply this for this problem? So for this problem, it's a two-stage process. The first thing I will do is to do a partial particle hole transformation. So I will call the A fermion is just C of I up, and the B fermion is C dagger of I down. So this is a particle transformation just in one spin sector. And I will be careful to put in the phase factor, which takes the value 1 on, let's say, one sublattice and the value -1 on another sublattice. Then I will ask that the H0 remains invariant under this transformation. And that has very, very severe consequences for H0, namely that H0 can only describe the hopping between two different sublattices. So that if I have a chemical potential, that won't work, right? Because chemical potential is like the hopping on one sublattice. So the chemical potential here, at this point, you see right away that if you put in a chemical potential for H0, it won't work. Now, so this is for this term, H0 has to be invariant under this transformation. And if you now do this transformation here for this term, then you will get an A dagger of I, A of I, minus B dagger of I, B of I, right? That's what you will get, because you're doing the particle hole transformation in one spin sector. And then you see that this is like a time reversal symmetry for the A's and B's, and that this term here will go to minus this term under time reversal symmetry, but you have a complex I here. So because it's anti-unitary, the minus term you pick up here will be compensated by the minus you get when you do the complex conjugation of the I. Right? So you can do the simulations. The point is that you can do the simulations for this Hamiltonian, and you will be able to show that there is no negative sign problem. And you can check it, right? You can debug your code if there's an error. Okay, so this is just very quickly, there's been a huge progress in understanding symmetries, understanding the absence of sign problem from the point of view of symmetries. And that's extremely useful because before starting the simulations, you can analyze your problem and see if there is a negative sign problem or not. If you can't do this, I'll come back later. What would you do? So here's an example of a
actually, may I ask a question?
With pleasure. Right.
Sorry, I'm a novice in this, so I just want to make sure I understood. Is the general lesson that if you have time reversal, the sign problems that you have are not as serious and can be dealt with if you pair things up in the right way? Is this
you don't have time? If you have time reversal symmetry or a symmetry for each field configuration here, then you don't have a sign problem. You can show that your fermion determinant is positive.
Okay, you just don't have one then. Okay.
You just don't have one. These are all symmetry correct considerations which suddenly don't have a sign problem. As soon as you have a sign problem, we'll come back to this later, then everything becomes exponential. Okay. Generically, right? There may be some special exceptions, but generically it becomes exponential in time. Good. So this is it. And so you can use the symmetry, and this is work we did with Toshio, who's in Würzburg, and Tarun, maybe Grover in UCSD, and you can play with these symmetries and say, well, let's write down some rather general models which are in the solid state rather remarkable because they're realized in nature. So this would be, for example, a Heisenberg model, which Uwe talked about yesterday. So these are spin 1/2 degrees of freedom, and I and J define a graph, right? So these are points on the graph, and the conditions I have for no sign problem is that J perp of Ij has to be smaller than 0, right? This is a condition, but this Jz of Ij can be arbitrary. So I could have classical frustration would be possible without putting in without generating a sign problem. So this is this class of problems is actually very rich in the sense that you can simulate, the isotropic Heisenberg model, as was discussed yesterday, and you will get, Goldstone modes, symmetry breaking, et cetera, et cetera. But you can also, if you, write it in a different way, you can simulate models which are called the balanced Fisher-Gervin model. And they are models where you have, it turns out to be a Z2 spin liquid, which means, I guess for you guys, that there is a low energy effective field theory, which is emergent, which is, it's a gauge theory, a Z2 gauge theory in a deconfined phase, right? So these are, this includes, if you want, this spin model includes ordered and spin liquid phases and disordered phases, etc. So it's pretty rich. Now, with these fermion Monte Carlo methods, you can also couple the spins to to charges, to electrons, and that essentially is what happens when if you have, let's say, a cerium atom has a localized F electron, just one F electron, which is like a spin degree of freedom, but it also has some S electrons which have which generate a band. So you have, think about things like cerium copper 6, for example. It's a mixture of localized electrons with what look like spin degrees of freedom and itinerant electrons, and these are what we call Kondo systems. So you would like to describe this, and here would be the simplest possible fermionic system, right? So this is a hopping. Again, what I will need here is that the hopping occurs only between different sublattices, so no chemical potential. And I've included a U-term, just a Hubbard U-term, with a very screened Coulomb repulsion. So this is also something you can simulate without a sign problem. No chemical potential, don't forget. And then you can couple those two, and you can couple those two by having some sort of, this is like a Kondo coupling up to this term between the spin degrees of freedom and the conduction electrons. Right? So this is a very generic Hamiltonian, which you can simulate, on which all our work on Kondo systems are done, right? So unfortunately, I won't talk about Kondo breakdown today, but that's the purpose of it. So sign problem. So what do we do when we have a sign problem? So the sign problem would be e to the minus of s of phi. That is something which now becomes complex. So I can't use this as a weight. Okay, so what should we do? Let's take the absolute value of it, right, and kick out the phase. Okay, so this here is just basically this. And then I'll do the same thing in the denominator, and I'll divide by this and this, right? Now, so this is an identity. And now what I will do, I will use the Monte Carlo to sample this blue thing. That will be my probability distribution that I will sample. And you see that I will rewrite this as the quotient of two observables. One is what I call the phase times the observable I had, and one which is basically the average phase. Now, why is there a sign problem? Well, the sign problem is what is the problem in the sign problem? Well, generically, you can say that this is essentially the partition function, right, of my initial problem, right? This is a modified partition function where I get rid of the phases, right? Now, in some cases, you can show that these are special cases, wordline type algorithms, where you can show that when you get rid of the phases, in a certain sense, for some cases, to change the fermionic degrees of freedom to bosonic degrees of freedom. This is a very special case, but let's think about it. And then you can at least follow the idea that this is the quotient of two partition functions. Now, partition functions are extensive in inverse temperature beta times the volume, so that the quotient of this, the average sign, is the quotient of two partition functions. And generically, right, you will get something, because the bosonic energy is lower than the fermionic energy in general, you will get something which is e to the minus beta, inverse temperature, n is the volume of the system, times delta, and delta is the difference, if you want, of the ground state energy per site between those two different systems. Right? So this is what you would get. And this has been checked for many systems, right? So this is okay. This is a bit heuristic, but this has been checked for many systems. So what is the problem? The problem is that we do Monte Carlo, and we would like, if we want to divide by something here, then the error on this object has to be smaller. So the error on z over z bar has to be smaller than the value of z over z bar. And so this has to be very much smaller than 1. But, so what I would need is that, but I know that, because I have the law of large numbers, the statistical error scales as 1 over the CPU time. And if I plug this everything in, then I know that if I want to control this very small sign, then if the CPU time has to be much bigger than e to 2 times beta v times delta. So I have something which is exponential. Okay? So any sign problem will ultimately be exponential. And you can say, well, that the method breaks down. Okay, so it does, in the sense that you go from a method which was something like which was a polynomial complexity to something which is exponential, so it's NP. So that's so it's bad. Now, is it really bad? It is. I mean, I won't try to say that the sign problem is good, but I'd like to say that, I mean, very often I have the impression that people say sign problem, ooh la la, that's it, that's the end of the world. It is the end of the world, but not completely, right? There are some things which you can do. And one thing is that delta is very much method dependent, right? So I can give you a problem with no sign problem, and I can do a formulation to generate a sign problem. And, delta could be very large, and then I could find a formulation to get delta to 0, right? So that's possible. Some cases it's not possible, and the question is, can we still do interesting physics when we have a sign problem? So this is a recent work which done with Toshihiro, who's also in Würzburg.
Question?
Yes, go ahead.
Why do you say that delta is method dependent? I thought delta is just characterizing the difference of the ground state energies between the bosonic.
Yeah, because you take the absolute value here of something which is the path integral is not method, the path integral is formulation dependent, right? So I take the absolute value here, and then that depends on the formulation I have, right?
Formulation dependent.
Formulation dependent, right? I can do different path integrals as you can do different mean fields, as you know. And so depending on how I do it, then I get something different.
Understood, because I thought you said, I guess you meant that by method dependent. Okay.
I'm sorry, formulation dependent.
Okay. Thank you. Yeah.
So this is a case where this is something which I think is pretty nice and very instructive. In our domain, there are some I don't know, maybe you guys know the Kitaev model. The Kitaev model is basically this. It's a model which is defined on a honeycomb lattice, right? So this is a honeycomb lattice, and I is the side of the honeycomb lattice. And if you have 3 types of bond. On bond 1, you have an SX interaction, SY interaction on bond 2, SZ on bond 3, right? Then we've augmented this by a Heisenberg term on the honeycomb lattice. So this is actually, this part here is an exactly solvable model, and has attracted a huge amount of attention because, one, it generates a spin liquid phase. Exactly, you see how the spin liquid phase is emergent from the Kitaev paper, and so that's very nice already. But that remains a toy model. It becomes much more interesting because there are some materials called Kitaev materials, right? Ruthenium chloride, trichloride, for example, where people believe that they're approximate to these to this Hamiltonian. So it's a big, these Hamiltonians, Kitaev models, and generalization of Kitaev models with Heisenberg terms and other terms which are relevant also maybe for in materials have become extremely popular in our domain. So the question is, can we do something with that? And the answer is, there is a sign problem. If as soon as I put in this term, I can never get rid of the sign problem. But what we can do is look at different formulations, and you can find formulations. So here it is, right? So normally you have a fermion determinant. We'll fractionalize the spin and have fermion basically, and you have a fermion determinant. And the phase of the fermion determinant basically can be something on a circle, right? So if you just do a formulation where you say, okay, the phase can take anything, right? Then you will get an average sign here, which is very bad. This will be this line. This is as a function of basically the angle phi, right? The angle phi is defined here, and you just basically just think about this term here. This term is this phi here is where you only have this term and not this one. This one is sign free. This one has a sign. Just think about that. Now you can do other formulations where you can say, well, let me be clever. If you want to have the details, you can go and look at this paper. And you say, well, let me take the determinant and let me find a formulation where the phase is only 0 or pi, right? That means the determinant is real and it only has fluctuations between, the sign is plus or minus 1, right? Just the sign fluctuations. Then you find out that by constraining the phase, that the average sign, which was here, pops up to be here, right? So you have a huge increase in the average sign. And then it turns out that before you get killed by this exponential decay of the average sign, you can get down to temperature scales, which are like beta A, which are of the order of 3. So you can go to 3 times smaller energy scales than the energy scales given by the model. So is this good or not good? Well, the beauty of this is that this model is already an extremely low energy effective model for these materials, and that the values of J's and K's are of the order of 10 milli-electron volt. Now, 10 milli-electron volt is of the order of 100 Kelvin. So we can go down to 30 Kelvin or 30 or 40 Kelvin with these algorithms, right? And it turns out to be something which is experimentally relevant. Since Monte Carlo is extremely good at doing thermodynamics, I think it may be a method of choice to look at thermodynamics of Kitaev model, right? So this is just an example to tell you that if there is a sign problem, things become exponentially hard, yes, but it is still possible to be competitive with other methods, and we're in good company, right? Because normally other methods in correlated systems are mostly exponential, right? To do ED, you're exponential. If you do tensor networks or 2D DMRG, you are also exponential, just linear in one dimension of the system, et cetera, et cetera. Okay, so let me now go on with the Monte Carlo part. I'm rather slow. I'm sorry about that, but okay. How do we go on, right? So let's now just forget about the sign problem and say there's no more sign problem, and we always have something positive. Have we solved stuff? I mean, in the sense of, can we are these methods good enough to cope with critical phenomena? Right? I think that's what could be very interesting. So here's the point. The point is that we have a determinant, right? We have this determinant here. And the determinant, there are 2 ways of coping with this determinant. There is a way which comes in the solid state physics, which is, well, we will just keep the determinant. And of course, as soon as you have a determinant, then you have some computational cost, which is to the cube of the volume. So L to the D is the volume. This is to the cube of the volume. So it's the best algorithms we have are those BSS algorithms. If we keep the determinant, will be the cube of the volume times L tau. Let's assume that you have so you have volume to the cube times beta. So you will have if you're looking at a critical point where the dynamical exponent is 1, so L tau has to be like L. So you will have something to the L pretty high, volume to the cube times L. So it's hard to get critical exponents when you have such a scaling for 2 + 1 dimensions. Right? So that you have to bear in mind. Question is, can we do better? And the better is coming from essentially high energy physics, where they, of course, in the high energy physics, and for QCD, lattice QCD, you're in 3 + 1 dimensions, and if you have this type of scaling, it will be really, really hard to get to big lattices. And there have been a lot of work done before actually the solid state physics community actually, which goes under the name of hybrid Monte Carlo methods. Now, the only way to get to progress, right, and to get better scaling is to get rid of this determinant. And the way that you do this in the hybrid Monte Carlo method is to say, well, let's stochastically evaluate the fermion determinant, right? So that's what is done here. And to do that, well, you can just use this Gaussian integration essentially, that you put in some new fields, right? You already have a lot of fields, just put in some new fields over which you will integrate stochastically. These are called pseudo fermions. And then m dagger minus 1, you have to evaluate this matrix. So I won't go into the details of that, but this algorithm is remarkable, but unfortunately is the way it works makes it very case dependent, right? So if you mean, if you get some type of scaling 1.5, volume times L tau 1.5, these are the best case scenarios. And then you have to cherry pick your systems where this really works out. In general, you won't get such an improvement, and you will see that the BSS algorithm, which has nominally a very worse scaling, becomes actually competitive. So this is we have these two methods, and depending about what you want to do, then you may want to choose this method, you may want to choose this method. Unfortunately, they're very different methods. The set of tricks are very different, and so it's not easy to do both at the same time. So let me go on and tell you one case where this method works amazingly well, right? And which I believe will give us a solution to an outstanding problem. And in the sense that we will be able to use numerical experiments to calculations to reproduce experiments. So numerical calculations, simulations to reproduce experiments. So this is the problem of essentially of graphene, freestanding graphene. As I told you before, freestanding graphene has a Dirac cone which looks like this, right? And the chemical potential is exactly here. Because the chemical potential is exactly at the Dirac cone, the Coulomb repulsion is not screened, right? Now, if you go to your solid state physics class, you'll see that to get a Fermi liquid, you have to screen the Coulomb repulsion. If you don't have screening, the Fermi liquid theory will break down, right? So this is actually what happens in graphene. Fermi liquid theory breaks down, and if you do RPA, you will see that, well, the velocity, which is just the number here for the free case, if you do RPA for QED3, for example, you will see that you have a logarithmic divergence of the velocity when you come to the Dirac point. So the question is, it's a logarithmic correction, it's a logarithmic divergence, so you have to go through very big system sizes to see that. And the question is, can we do that with the numerics? So here is a beautiful piece of work which is done by Maxime, right? And Azafas and also Christophe. And Maxime is the person who really did the HNC calculations. And here's the question, right? So we have the experiments on freestanding graphene, and this is the velocity renormalization, if you want, when you arrive to the charge neutrality to the critical point. Okay, I'll show this to you afterwards. Now, there is one thing you have to know those experiments, how do they work, right? They actually they do the experiments, when they're here, that exactly the charge neutrality, right? But when they want to calculate the velocity here, they dope the system a bit. So they go away from the half-filled case, they dope the system and calculate then the velocity, basically, or the Fermi surface, if you want, at a finite doping. Now, of course, when they do this, they introduce finite doping, so they introduce screening of the Coulomb repulsion. So they do a big change to the system, right? So please keep that in mind. So that the logarithmic divergence they see should only be confined to very, very small dopings away from half-fill. Now, okay, so that's the experiment. Now, how we would like to reproduce experiments, and of course, if you look at graphene has there's no screening, as I told you before. And so the long range part of the Coulomb repulsion is like a bare, just the Coulomb repulsion in vacuum. But the short range will be screened by higher energy bands, which will, you will have particle hole excitations to higher energy bands, and you will screen the short range Coulomb repulsion. So there are methods in the solid state community to try to take into account the short range screening of the Coulomb repulsion because of higher energy bands. And these things go under the name constrained RPA. So this has been done in this very well cited paper. And they come up with these values of the Hubbard interaction, next nearest interaction, next nearest interaction, etc. So we will just take these RPA values for the short range, and take the short range and then start with the short range and then add a Coulomb tail systematically to get our model parameters. Okay, so this is what we do, and then we just do the calculation, and they calculate the single particle spectral function, and for the experiments they carry out a finite doping. What we do is we do the calculation at half filling, do a rigid band shift, so we don't change the chemical potential, we just do a rigid band shift corresponding to the particle number, the experimental pencil have, and then we calculate there at this energy the velocity, right? But just doing the numerical differentiation of the dispersion relation. Okay, so that's what we do, or Maxime does, and here's the result. And the result is absolutely, in my opinion, remarkable. This is the experiment, right? This is the density away from half filling. This is the experiment, right? And so this is what you could say this is a log, right? So this is a log, semi-log scale. This is a log, right? And then the experiments, they drop off the log. And one interpretation for this is that because they dope the system, the Coulomb repulsion will be screened, and then you get, the log will basically break down. So we have an understanding of why this breaks down here, right, at this level. Good. So this would be the experiment. This is the calculation. So the calculation is done on a huge lattice for us. It's 102 times 102. Unfortunately, still at rather high temperature, so that would be 600 Kelvin, right? So that's pretty high temperature still compared to the experiment. But nevertheless, at high energies, you see that these are the points we have here, and you can put a line from here to here, and you see that it sort of fits, which is there are no fudge parameters. Right? We just basically took the data from the paper I cited before. Okay, so how? Of course, this is the Monte Carlo. If you go to lower energy scales, the Monte Carlo start to deviate. We believe that these are temperature effects, so we have to go to lower temperatures. And it's possible if you want to go to even bigger system sizes, right? So 2.4 and lower temperatures are in the workings now, so these are running. So if we get these calculations done, then we will be essentially able with this HMC to bridge the gap, between experiments and theory. And then it's pretty cool, right? Because we can then go to the experimentalists and ask them to work a bit better. Maybe they won't, maybe they will, I don't know. But what's also more interesting is that this is an experimental and a numerical realization of, of course, it's discretized of QED3. And then you can, gauge the perturbation expansions of QED3 in a case where alpha is very big, if you want, to the to experiments or to numerical simulations. Okay. So this is what I wanted to say about this HMC and the possibility of going to very, very big lattices with HMC, which is rather remarkable for Fermi. Don't forget it.
Could I ask a question?
Pleasure. Yeah, go ahead.
What is N? What is the x-axis?
Sorry, I was too quick. The x-axis is, if one, is the doping, right? So if I have a Dirac cone like this, right? So zero doping, that would be here, and then I would push in the chemical potential like that, right? And that will give me, if I will fill up everything to here, and the number of electrons I have in this domain is basically the N, right?
So how
sorry?
How come then your Monte Carlo simulation has higher doping than the experiments? I thought.
Yeah, because what we do with the fermion Monte Carlo, we essentially have this, right, and we only have some couple of points here, right? Because we're on a finite size system.
Okay.
Right. And so what we do, we calculate these points here when being at half filling, and then we just manually put the chemical potential here, right? And the chemical potential here, we have the dispersion relation, right? So if I have the chemical potential and you know the dispersion relation, then I can calculate the N, right? Mm-hmm. I can calculate the number of electrons I have, right? And then for this chemical potential, I can calculate the velocity renormalization. What is the velocity of the dispersion, right? So the energy I put in here defines the N. I mean, if I have the energy and the dispersion relation here, I know what the N is. And then at this energy, I can look at the derivative of the dispersion relation, and that gives me then the velocity. Right? And of course, at one point, since I have a finite lattice, I don't have any more points. I have a discrete set of points. And so I'm stuck, right? Then you're stuck. So there's a cutoff. Okay. So that's what's being done.
So that's why you're saying you have to go to larger volumes.
You have to go to larger volumes to be able to. I mean, you need larger volumes to resolve the small energy scales. Mm-hmm. Right. That's what I'm saying.
you.
Okay. Let me move on a bit. Yeah, let me move on because I will be too slow. We have, if you're interested in those Monte Carlo BSS, we're developing a package. It's online. It's open source. I won't say so much about it. It's complicated to use, but it's very general, and we're here to help if you want to use it. We're doing our best to make it easy to use, but it's not always easy to do that. Okay, so this I will skip, and I will go to my first subject. Otherwise, I will not. How do we do with a break? The break is we still have a bit of time, and then maybe take 10 minutes and a 5-minute break. Would that be okay? Yeah.
Yeah, that sounds good.
Okay, so let me go on. So skyrmion superconductivity, right? So let me tell you. Let me start with the motivation of why this would be interesting. And what it means. So here we start with Dirac fermions, right? So we're basically hopping on a honeycomb lattice, which gives me in the continuum gives me this Hamiltonian. Those sides are 4 components. Dirac's sigma is the spin, so I have 8 components now. And so now on top of this, we can add some basically at each origin of the hexagon, right? We add a vector n of x, which is normalized, and this n of x couples to this object. Now this object is a discretization, if you want, of a Haldane mass, right? So Haldane mass is something which is I, gamma 0, gamma 3, gamma 5, if I remember well, right, in my notations. And it's a couple times the spin, right? So this mass term here opens a gap, right, in the for the Diracs, right? But it's a gap, it's a non-trivial gap in the sense that at the edge of the sample you will have some edge states, some Dirac cones, 1 plus 1 dimensional Dirac cones at the edge. So if you do this, if you just take n of x here is equal to E of EZ, right? And so this is basically, apologies, here you have 3 of these mass terms, which is sigma x, sigma y, sigma z. So it's a three mass terms here. Here you just pick up one of the mass term and everything's constant in the sort of spin in the SO3 direction. So if you just take n of x equal to EZ, then you get what is known as the Kane-Millet Hamiltonians, basically 2 Haldane Hamiltonians, but with different Chern numbers and different spin sectors. And okay, it's a mass term, so you open up a gap in your density of state. It's a chemical potential. It's an insulator. And if you put everything on a system with open boundary conditions, then at the edge you have then this is a helical liquid in this case. Spin up on one edge goes to the right, and spin down on the same edge goes to the left. Right. So this is the Kane-Millet or quantum spin Hall state. So everything is fine, etc. Now, and that's what you have in experiments. Normally, you have an n of x, which is a constant, which is given by the crystal, by the spin orbit coupling, etc. Now, let's ask the following question and say, in principle, the spin orbit coupling could be dynamically generated by some interactions. Right? Now, if this spin orbit coupling is dynamically generating by some interactions, then I will have to start to think of n of x as a dynamical vector, which would have some Goldstone modes and also some topological excitations, right? So some topological structure. So let's follow this idea, right? And the idea, this is the idea. So let's play around with this very simple model. This is still the motivation. And let's put in a skyrmion. Let's just take a skyrmion n of x here, right? Just this is in skyrmion. I'll put, the calculation I'll show it to you afterwards is 36 by 36 lattice. Senju did this work, right? Did the calculation here. So you have your spin, your n of x, which points up, right, in the center. And then if you go away, it goes like a vortex, right, in the xy plane. And then if you go very far away, it goes negative z, right? So I can put a single skyrmion on my, say, 36 by 36 lattice. And I have a Pontryagin, I don't know how to pronounce it, index, basically a skyrmion count, which is basically just 1. Now, what happens to this is that, let me do the calculation. If you put in this skyrmion and you break particle hole symmetry, you can show this very, very, very easily. And you see that you have transferred two charges or two holes from the lower band to the upper band, right? That's the result of the calculation. You still have a gap, and you have transferred two holes. So that means that the skyrmion has a charge, and the skyrmion has a charge 2e, right? And you can see this. There's a very nice calculation which is shown in this paper. You can see this, and basically start with your skyrmion here, right? And systematically go into a system, right, where n of x is basically just in the x direction. So you twist as a function of x your fermions, right? And what you will obtain out of this calculation is basically a time reversal magnetic field, and that's the jargon of solid state physics. I'm sorry, and which will pump exactly 2 electrons from the lower band to the upper band over the edge when you do this, when you go into a reference system. That's where I was looking for, where n of x is just in the z direction, right? So it's like it's a pumping argument that you can understand why you transfer 2 electrons. What's interesting for us is that we have skyrmions, and the skyrmions are, I mean, if we can generate this thing dynamically, then we have skyrmions, and skyrmions will carry charge 2e, right? So of course, you can then follow the idea that if I can condensate the skyrmions, then I should be able to generate some type of superconductivity, right, out of topological excitations of a topological dynamically generated quantum spin constant. That's the motivation. Okay. So that's very nice, but our job is to find a Hamiltonian which will do that for us, so that we can really see if this idea works and if fluctuations work out as we want. So this is the Hamiltonian we came up with, right? And which seems to work. And so it's the same Dirac electrons. I'm summing over all the hexagons of the honeycomb lattice. And for each of these, on each of these hexagons, I have this discretized version, if you want, of the K Mealy mass term, the 3 mass term. So this is a vector, right? And I just square it, right? And by squaring it, then we restore all the symmetries. Right, so this is a symmetry. This has basically a SO3 symmetry. So this is the model point. That's the model, and then the question is, will the model do what we want it to do? So to capture the dynamically generated quantum spin Hall state, what we calculate is this vector J. So this is an SO3 vector, 3-component vector, which is which is defined on the hexagon, and you sum over the next nearest neighbors of the hexagon, these sort of a spin orbit coupling term, right? So if J, gets basically the expectation value of J is just corresponds to n, right? That's just the vector I have in mind. That's all there is to it. Now, because we have skyrmions, maybe we don't know yet, but because we have skyrmions which maybe carry charge 2e. Then we will also calculate an S-wave superconducting order parameter, right? And that will be it, to see if we can pick this. Okay, so that's what we will do. So let's start the simulations. And the simulations, what we do is so we start here. We just start from the semi-metal. We prop up lambda, and then just look at what we get. And what we calculate is the spin, the susceptibility, if you want, of the. So this is the generalized susceptibility of this quantum spin Hall order parameter. And the way we analyze the data are some things which we use what people call the correlation ratio, which I think was the first time introduced by Ribou. And it's the correlation ratio is a renormalization group invariant quantity. So that what you do is you basically look, let's assume that we have order at the wave vector Q0. If I have order, then this will diverge at Q0. This will diverge, but less quickly if delta Q is a very small wave vector, which goes to 0 as a function of system size. But then, this will basically go to 1, right? This will diverge quicker. If you have a disordered state, this is a uniform, this is a smooth function. So if I take delta Q to 0, so this will go to 1 and have something which is 0. So it's equal to 0 in a disordered phase. It's equal to 1 in the ordered phase. And then, but if you assume some scaling, ansatz for the order parameter, then you can show that this quantum spin Hall is a renormalization group invariant quantity. That means that it scales as L to the Z divided by beta, the distance from the critical point, L to 1 over mu, and then these are the leading corrections to scaling, right? So what this means, if I just plot this correlation function as a function of lambda, right? If I claim that corrections to scaling here are negligible, then I will have a crossing at lambda equals lambda C, and in fact we do, right? So this will be my more or less my lambda C, and you can extrapolate the lambda C to thermodynamic limit to get this value of lambda C for this transition between the semi-metal and the quantum spin Hall. Okay, so that's how we do our work. So what about the critical exponent? I mean, so this semi-metal to, yeah.
We continue. Just I was a little bit confused how you got the model. Did you integrate out somehow n field randomly, and that's how?
No. I just write it down.
Okay, but
Just write it down.
Looks like the previous model, except you kind of integrate and
yeah, exactly. That's exactly the motivation.
Okay.
That's exactly the motivation. That's the motivation. Of course, I would n, yeah. If I integrate n out, I put it basically an n squared term, and I integrate it out, and I would get that. I agree, right?
So that would roughly correspond to skyrmion condensing. That's what you hope. Is that?
That's what I hope. That's what I hope. The problem is that when you really do the calculation, you calculate the square term here, then you get tons of trash terms. You get tons of terms, right? And it's highly non-trivial to see which one will dominate, if the skyrmion will really dominate. And actually, we did. Thanks for the question, but you know, this is a pretty big thing to do, right? You know, it's a big object, right? And we didn't start with this. We basically started with let's just put the quantum spin Hall current only on these things, right? Only on this. Oh, I can't do this. How do I do this? Only put the quantum spin Hall only on these bonds here, right? Right, to get some smaller interaction, and then we only got superconductivity. Right? So it's not the argument. Okay, so the point is that if the point is the following: if I put in this term here just on a hexagon, then I can define another model where I can put this on the three adjacent on three hexagons, right? On a thing which is like this, on a bigger part, on a higher range, right? So I could basically put in the K-Mealy term on this, and this, and it's not very well drawn, and then put it to the square. So I enhance the range of my interaction. And if the range goes to infinity, I get my mean field, which I had before. Right? So this is the logic in how we build these models, right? You start from a mean field, you say, well, to get the mean field, I need some long range interactions, but I would like to put in some fluctuations back in, right? So I reduce the range of the interaction, get more and more fluctuations, hopefully not losing the phase, right? And then then it's a question of luck. Will it work? Will you get some nice physics out of it or not? And since I'm showing it, we do get some nice physics, right? I mean, for this one. Is that okay?
Thank you.
Okay, so that's the point. And now let me just go. Let me just go to this part before continuing. Take a 5-minute break. The point is the following: what type of transition do we have from the semi-metal to the quantum spin Hall? Well, that's a very I believe well-known Gauss-Neveu transition. An SO3 transition, which is exactly the same type of transition you will have if you have a semi-metal to a AF QMC, antiferromagnetic AF antiferromagnet. And so there's a big history. This plot is there is a huge industry in our domain and also in epsilon expansions of how to calculate those exponents. And it's this is a table. This is our study for this quantum spin Hall. This is a study from Sandro Sorella, a very recent study of this year also of Sandro Sorella. You see that we do get more or less the same exponent as he does. This is basically a transition from a D-wave superconductor to an AFM, right? So it uses a D-wave superconductor to generate the Dirac system. This is work from HMC from Pavel Budidovich. I don't know how to pronounce his last name. Pavel Budidovich, if you know him.
Budidovich.
Thank you. I'm sorry, Pavel, if he hears this, right? Very sorry. These are older works from Sandro Sorella, etc. So you see that, and this is organized as a function of time. So you see that as a function of time, we seem to be converging more or less to the exponents. And also, if you're generous, right? These are fourth order epsilon expansions. These are remarkable calculations done in the group of Michael Scherer and Kohn and people around them. And so they also have the same, more or less the same exponents. Anyway, so the exponents are those of the Grosvenor O3. And so it's not very, the transition is not very interesting. So what is interesting are the excitations, and that's what I'd like to discuss after. Maybe should we take a 5-minute break? Right?
Yeah, sounds good. So meet again at 10:05 then?
Yeah, perfect.
Okay, see you all in 5 minutes.
Well, I'll stay online if you have questions. I'll quickly get something to drink. I'll stay on.
Okay, excellent.
I have a small question, if you.
Yes, go ahead. Hello.
Yeah, just the Grosvenor O3. You mean the one with like three scalars coupled Yukawa coupling through
Exactly.
polymetrics. Yeah, I see.
So what I mean is basically a psi bar, a G psi bar, and then it would be a sigma.
Yes.
So that would be something like a psi dagger, gamma 0. Right. That would be it.
I see.
Right. And then basically d mu, gamma mu, psi bar, psi plus this. That would be the Lagrangian. And then plus the Lagrangian of phi to the fourth for the right. I'm sorry, of course, coupled to the field, to a three-component.
Yeah, coupled to the thing. Yeah.
Three-component field, and that would be the phi to the fourth theory for the two.
I see.
But that's what I mean.
I see. Thank you very much.
And then the claim is that if this would be these are three mass terms, right? And if you replace those three mass terms by sigma and then I gamma 0, gamma 3, gamma 5, right? So these are the three mass terms for the spin instability. These are the three mass terms for the quantum spin Hall instabilities. And then I think that Igor Herbut has shown that in every order of electron expand. I forgot exactly what that. These are the same. These are the same. Basically, there are no distinctions, right, between universality constants.
I see. I see. I see.
Right.
All right. Thank you. That's very clear. Yeah.
Okay, it's 5 past. Shall we begin again?
Sure.
Okay, great. Take it away. Thank you.
Okay.
Can you give us just 1 minute?
Sure.
That's okay.
Sorry.
We're coming.
Okay. I saw Iñaki enter the room, so I figured you were just out of range of the owl. Actually, perhaps in the meantime, Fakher, could I ask you a quick question about to make sure I understand the phases?
Right.
In quantum spin Hall state, the SO3 is spontaneously broken. Is that
Exactly.
correct?
Exactly.
Okay. And the electrons are gapped in that
Yes.
state?
Yes.
Okay.
There's a single particle gap. So it is if you look at it's a semi-metal to insulator transition. It's a dynamical mass generation, right?
Okay.
It's a very principle, very textbook like.
Okay, great. Thank you.
Yeah. So I'll show you this after, right? So whatever. So this is the so now we would like to, so we have this transition, we have this quantum spin Hall, and now we would like to understand, do we have skyrmions, right? Do we really generate the skyrmions and this link between skyrmions and charge? So what this plots, so I'm putting myself in the quantum spin Hall phase here, right? I'm putting myself in the quantum spin Hall phase, and I'm measuring the single particle gap. So that was exactly your question, right? So there is a gap if I try to put in an electron, there's a gap. Now, what I can also do is I can try to put in a pair, right? I insert a pair into the system, and in principle, I divide the energy I take to put in the pair to the system divided by 2, and you see that it's smaller than the single particle gap. So putting in 2 electrons, right, is less energy than putting in a pair, which means that the 2 electrons bind, and I have binding, right? So that's the aim of this plot, that we have binding. So if we have binding, is the pair, so the lowest energy is a pair, and is this pair a skyrmion? Right? That would be the question. So it's a bit, so it's not so. How do I image the skyrmion? So that's, that becomes a bit okay. So that's what we do, and you tell me if you agree or not with it. So we're motivated by this equation that the charge, right? The charge, basically the dark density, is related to this to the structure, if you want, the curvature of this n vector. Okay, so what we do is we modify our model and say, well, let's the skyrmion is, the charges are everywhere, right? So I have to localize the skyrmion. So what we do is we normally have a chemical potential which is 0, and then we just do basically a trap, right? We change our chemical potential, we do a trap, right? So that's 2 electrons, the 2 holes we dope, they fall into this trap, And then you have to, there's a bit of chemistry, right? The trap has to be big enough to be able to localize, etc. So you have to play around with parameters. I'll be very honest with that. And then once we've trapped the electrons, right, the two holes, the pair, right, then we can measure around this. We haven't broken the SO3 symmetry. We've just broken the translation symmetry. That's all we've done. And then we just measure the real space spin-spin correlations around the whole pair, right? And this is it, right? So the spin-spin correlations, I mean this J vector, this is the origin, right? And so you see that at the origin where I have my holes, this is the correlation is positive, right? So it's basically, if I try to draw this, the correlation would be, for example, in the Z direction up here. At the edges, this is blue, so it's negative. So it's in this direction, right? And at one point, if I have a skyrmion, then here it should be, this would be the vortex, right? And since I did not break the XY symmetry, I basically don't see anything. These are orthogonal to this, right? So I have the possibility, at least, of interpreting this really as a skyrmion. That means that the charge and that we really have this skyrmion. So this is, for the moment, the best we can do to understand, to get something very clear. If you do the same calculations here, you will not see this.
Can you explain? So what is the plot? You did the simulation.
Yeah. So we have. Okay. So let me start again. So here, that's what we've modulated the chemical potential. Okay.
Okay.
Okay. So then if I look at the charge, then my electrons, they are here, right? My two holes, they're basically here. Okay. They're trapped.
Okay, I think I understand now what you mean. You say I want to kind of mimic the skyrmion by changing the chemical potential.
Exactly, right? So the point is that what we want to test is the link, right? What is interesting to test is this equation, which gives you the link between the charge density, right, and the SO3 vector. Right, so that if I localize, so I play with this, I localize this, and I measure this. That's what we do. So we localize the charge, right? So the charge is localized around here. And then once we localize the charge, then we can say that, well, if this is okay, then we've sort of localized the skyrmion, and then we go in and calculate the spin-spin correlations around the center where we localize the charge, and we do see something which would be compatible with what we expect for a skyrmion. Okay?
Okay.
Okay, just hope that this makes sense.
One thing that
Yeah.
confused, you simulated the model, which I was under the impression that it already had, it was a disordered field that you integrated, generated these interactions. I mean, the skyrmion should have been already there.
It is there. It is there, but how do I image it? How do I image it? You see, the question is always, how do I, I have these words, etc., but I like to see things, right? I mean,
It's part of the system already, so I don't know whether you can. I mean, if it's completely disordered everywhere, you can't really.
Okay, so I think maybe I can. I think if you have those world line algorithms, I think you also collaborate with Anders on this. Maybe Tim, I forget, but you can do. I think what Anders does are snapshots of the configurations, right?
Exactly.
Right, so you do snapshots of the configurations, and out of these snapshots, you try to look at vortices or spin-ons or I don't know what. Right now, here it's rather complicated. We have a field which is, if you look at the snapshot of the field, well, we should do that. But the point is that we maybe don't see so much, right?
No, I believe that.
I mean, we're not very close to the simulation, right? I mean, if you do world lines, you're very close to a spin. Here, we're rather, we do the Hubbard automata decomposition. We don't have a real field. It's a discrete field, et cetera, et cetera. So it's maybe hard to do that. And that's then the best thing we could do was to localize this, right? So what you could do for the JQ model, for example, you could impose for the JQ model. What you could do is you could have here would be a JQ model in the VBS phase, right? And in the VBS phase, what you would do, you would say, well, I take one VBS phase here, another, I pin it here, I pin another one here, I pin another one here, and then you measure the spin density here, right, in the middle, and you should see a spin-off, right?
That's right. So here you're
idea.
one spin-on in the system, but you're not localizing it anywhere, right?
You're not localized, but if I have a finite system, right, and if I have a finite system and I localize a vortex by playing with the boundaries, right, then I will, I will generate a spin-off.
That's right. That's right. So you're essentially, in that case, you're essentially looking at the sector with the finite charge.
Right. Exactly.
Charge.
Right.
Is there an analog in your system of that to do the simulation with one skyrmion charge, because that is a conserved number?
So this is a simulation with one skyrmion charge. This is a simulation with exactly 2 holes.
Okay, so this is how we want to interpret it, but
Yeah.
you're putting a profile for the chemical potential, and depending on whether, and that's pinning the.
Yeah, I have to pin something, right? Exactly like the thing for I have to pin something. So I have to pin the charge. And so we pin the charge with a profile of the chemical potential.
Well, the other thing that you mentioned with the boundaries, it doesn't pin it in any particular place. It can still move.
It can still move, but it will have, okay, it can still move, and you have to be careful about, okay, it can still move, but if I do this, okay, so put it that way. If I do this calculation and I pin it, and I calculate here the spin susceptibility, right? As a function of temperature, I calculate the spin susceptibility, then I should get something which diverges, right? Because you would have a 2-fold degenerate ground state, right? So you could do that. And then you would not have to localize it. I mean, that would be one possibility. And as soon as you take away the pinning away, then this would be a gap state, right?
Okay, I didn't mean to hijack.
No, I prefer chatting than talking alone. That's funner. But maybe that's not the point. You're the organizer, so you tell me what to do, right? So I'll go on. And so this is our skyrmion, and then we got interested in what type of transition. So this is pretty unique because we have an insulating state which has a Goldstone mode. I didn't show you this, but it has a contains broken symmetry. It has topology, etc. And then you would like to dope it, and ask yourself the question: well, what happens? And if you think about mean field, then you can have a first order transition between those two things. You can have a coexistence, etc. These are basically the two things you could have. And what turns out here, so these are plots as a function of doping, right? And this is the superconducting order parameter, and you can go through these plots, and you will find that as soon as you dope, you get an S-wave superconductor. So I dope here a tiny bit, I get an S-wave superconductor. So the interesting question then is, that's not surprising because you have pairs, the pairs will condense, etc. Right? Then the question is, what about the quantum spin Hall order parameter? And these are the correlation ratios for the quantum spin Hall order parameter as a function of delta. And what we see is that as a function of increasing system sizes, that's 24 by 24, then the crossing, which will tell me that on the left I have something ordered, on the right I have something disordered, this crossing systematically moves to delta equals 0, right? So that's what we can see. And we can also calculate in the disordered phase, we can calculate the length scale of the quantum spin Hall fluctuations. And you see that this length scale is always growing, right? It's never saturating here when you approach the quantum spin Hall insulating state as a function of doping. So this is a transition which seems to be, so this is an interpretation of the data, and then up to you to decide if you want to believe it or you think that there is another scale which kicks in and changes everything. That could be. We claim that we see a direct and continuous doping-induced transition between a quantum spin Hall insulator and an S-wave superconductor, right? And our resolution, so we can give a resolution. Our resolution is 2 holes on 24 by 24 lattice, right? So if something different happens, it's below this resolution, which is a rather good resolution if you think about, dopings we had for, in the domain of high temperature superconductors, etc. Right? So the picture is the following. You have your quantum spin Hall phase. You basically dope it. These are skyrmions, right? The skyrmions proliferate and mess up what you want the order. That's the picture I have. This is not a DQCP in the sense that there is no particle hole symmetry. There is no Z is most probably not equals to 1, etc. So I think it's an open question to understanding this critical point as a function of doping. I think I believe is open, right? I mean, at least I don't know how to write an equation for that.
Sorry, may I ask a question?
Yes, please.
If I understand, you went up on this plot and you entered a superconducting
Right.
phase. Is that correct?
Exactly.
But in this picture, it seems like you've continuously connected that phase to the SM stands for semi-metal. Is that correct?
No, that's not really correct.
Oh, sorry.
That's my fault. The semi-metal only works here.
I see.
Semi-metal is very special because you have zero density of state.
Okay, sorry.
So
Okay.
the superconducting, the
Yeah.
superconductor is everywhere. Now,
Okay.
we will
Okay.
talk about skyrmion superconductivity here, but if you go way out here, then you will lose you have interesting crossovers between skyrmion superconductivity and just normal BCS superconductivity.
Okay. But the phase is the same. It's just a normal.
The phase is the same, right? It's like it's the same phase, right?
Sorry. Okay. Thank you. I understand. Yeah. Great.
Okay. So now, so this is new, and then I can go on a bit. So this is something which is bandwidth control. We change the chemical potential. The next question we want to ask is that can we stay at half filling? So we stay here and then go from the quantum spin Hall to the superconducting state. And that would be something which would be more like a generic DQCP. So how should we do that? We don't want to change the chemical potential. We want to change something in the model that makes the skyrmions or these charged 2e objects condense. And so the obvious thing you can do is to add an attractive view to the model, right? Add an attractive view, another axis. This will be our semi-metal. This will be the quantum spin Hall I showed you before. And then here somehow you will get into a superconducting state, right? And you will be interested in this type of transition. Now, it turns out, this is luck. It turns out that we don't even have to do this. And that if we just continue and prop up our lambda, then this quantum spin Hall state is actually only an intermediate phase. And we go to a superconductor here. So here, this point, that's what I'd like to show you, that it really exists. And this point should be a candidate actually for the DQCP. So these are more of the same plots. If I go too fast, just interrupt me. So this is this correlation ratio for the quantum spin Hall. So I start in the quantum spin Hall state, it goes up. I go here to the superconducting state, it goes down. So I have a critical point here. I do the same thing for the super correlation ratio, but for the superconductor. Here it goes down, that's the quantum spin Hall state. Here it goes up, I have my superconducting state. And what is very important is this inset here. Does this happen at the same point? Are these two things which happen at the same time? And you can look at the crossing as a function of system size. This is 1 over system size. This is the crossing for the quantum spin Hall transition, for the superconducting transition. And well, again, we can interpret this as being at the same point. Now, one thing which is very important for the theory is that, is this a bosonic or a fermionic theory? And it turns out it should be a bosonic theory in the sense that if you look at the single particle gap across the transition here, right? The single particle gap remains open across the transition. So this is a single particle gap as a function of 1 over L. The transition is around here. So you see that we have a big single particle gap, it remains open. So this is basically now a transition where the fermions play no role, essentially, right? So it's more like JQ type model. And so what we have now is as a function of lambda, the semi-metal I showed you before, this Gauss-Neuville O3 transition, and then here a direct and continuous. I mean, we see no sign of first order transitions on our lattices, direct and continuous transition between this quantum spin Hall and the S-wave superconductor. Okay, so this is a bit of, I think I could go quicker here. This is not a Gauss-Landau order parameter theory-like transition, because you would have coexistence first order or an intermediate phase or some very ungeneric continuous thing. If you do, because of fine tuning, right? If you do mean field for our model, so this is written up in this paper if you want. If you do mean field for the model, then you get at mu equals 0, you get a wonderful coexistence of the quantum spin Hall and the superconductor. So nothing which extremely far from the Monte Carlo, right? So this is just order parameter theory. So everything seems to be working for us, that there's something more to it. And of course, that's what I showed before. It could be a DQCP, right? So this is the picture you have when you have the C4 ordering, right? The C4, the JQ type model. And I'll show you this afterwards. Basically, that in the DQCP you have a symmetry which is an SO3 times Z4, right? At the critical point, this SO3 times Z4 gives ways to, that's the claim, to SO3 times U1. The vortex of the U1 essentially gives you the spin-off, right? And that's what is shown. That is what is shown, right? And at the critical point, this spin-on is deconfined, right? It's an object, of course, which carries gauge charges, and it condenses to form the order in the ordered phase, right? So that topological defects of one phase carry the charge of the other. That's the idea of DQCP. So a very elegant way of seeing this from Dirac fermions comes really from a paper from Tanaka and Hu, and also later on a paper of Matthew Fisher and Sento. And of course, all this is based on the work of Abenoff and Wiegmann, right? On how to integrate out fermions in massive Dirac systems. So the point is the following: is that you have this beautiful algebra of mass terms in Dirac systems. These are my three quantum spin Hall mass terms. They all anti-commute, right? And then I can pair them up if I'm in 2+1 dimensions with two 4-component Dirac fermions. I can pair them up with two other mass terms. And these are superconducting mass terms. Pairing up, that means that I have a quintuple of 5 anti-commuting mass terms, right? So that's just playing with Legos. I just enjoy doing that. So this is a bit more complicated because there's a Bogoliubov index, etc. So you have 5 mass terms, right? And you would like to do a theory, a Gauss-Neveu type theory of these 5 mass terms. So how do you do that? You start with your Dirac, then you, as I told you before, you have a Gauss-Neveu type interaction where you have a 5-component field, phi here, which couples to those 5 anti-commuting mass terms, right? And so you can believe that this type of action can give you, of course, the semi-metal if this does not condense, phi 0. If you have, if it points in this direction, it's a superconductor. If it points in this direction, quantum spinel, etc. Now, this system here, just the Dirac, because of the anti-commuting properties of the mass terms, has an exact SO5 symmetry, global SO5 symmetry, meaning that if I do an SO5 rotation of this 5-component vector, I can show there's different ways of seeing it. If I do an SO5 rotation of this 5-component vector, it's like doing a canonical transformation for my size. The consequence of this is that the single particle gap, right? These are mass terms. The single particle gap, because of the SO5 symmetry, is just given by the norm of this SO5 vector, right? That's the point. Now, if I want to look at this transition here, right? If I want to look at just this transition here, I showed you numerically that the single particle gap does not vanish. That means that the norm of my vector remains constant over this transition. So if I want to proceed, right, then I can say, well, I can only look at the phase fluctuations of this phi and forget about the amplitude fluctuations because they never close, right? Of course, this Lagrangian is only complete if I put in the dynamics of this 5-component phi field. My Hamiltonian has an SO3 times U1 symmetry, so this could be broken down from SO5. So this term here breaks down everything from an SO5 to SO3 times U1 symmetry. Good. So now we can follow Abenoff Wiegmann or Tanaka and Hu or Fisher and Sento, etc. And you will just integrate out the fermions in the large, in the limit where you have a big mass gap, do a 1/, mass gap expansion, and you will get your topological, your Wessel-Witten term. Right? So this is the term, right? This is a topological term. It has no scale, etc. And so the only scale you will get out here is basically, of course, you have the SO3 times U1, the stiffness of this 5-component order parameter, and this topological term. So what does this? I mean, these are just, well, okay. So what do I do with this? How do I see that this is something? So I instead of the only thing I can do to understand things is to do explicit calculations. So this is a calculation you can do, and you can. This is taken from Charwoon's paper with Sento, and you can basically say, well, let's just play with this term. I think that's the only way to demystify this term is just put in a configuration, play with it, and do a calculation. What this is showing is to say, well, let's take two of the components, right? So you can go for the details in this paper. take two of the components of this 5-component field, so that would be the number 3 and 4, and then do a vortex in those 5 components, right? So at infinity, you have, you just take two, you have two spatial dimensions here, which you characterize with polar coordinates. At infinity, you will have a vortex. And then when you come to the origin, that means r goes to 0, then everything will go into the 3 directions, which are the remnant, right? And those 3 directions are characterized by a vector n of tau and u. U is the, basically everything which deforms the physical field to the North Pole, as we have in the Semino-Witten terms. I'm sorry if this is a bit quick. So you can plug in this configuration. You have some assumptions on alpha, right, to generate the vortex, and to be sure that when u equals 0, everything goes to the North Pole. You just plug this in, do the calculation, and what you obtain is essentially the quantum Berry phase, exactly the quantum Berry phase of your spin 1/2 degree of freedom. So this is the maths, if you want, which is behind these cartoons, right? These are really cartoons which are very appealing. But if you want to go beyond that, and if you don't have if you want to see that, then basically this is the math which is telling you what to do. So the point of this part is to tell you that, well, we have the field theory, which could understand another way of understanding the DQCP is through those Dirac fermions. And the nice thing of this Dirac fermion approach is that if I, instead of taking a quantum spin Hall mass term and a superconducting mass term, I take the 3 AFM mass terms here. These are 3 of them, and I take the 2 VBS mass term. Then essentially I will go through the same calculations and get exactly the same field theory, which I believe would then describe the critical point. So what this tells you is that the critical point of our model, quantum spin Hall to superconductor, should be exactly the same as the quantum critical point from the VBS to AFM, modulo all possible complications, which I won't talk too much about. So what we did was to look at critical exponents and compare those critical exponents to what Anders has and also Adam has. So this is the anomalous dimensions. I think they come from Adam. This correlation length comes from Anders' paper here. These are JQ and loop models, and this is what we get for our transitions here. So you see that some comments are in order. First of all, our error bars are bigger because we're working with fermions. That makes things very hard. So we can go to 24 by 24. God knows how far Anders goes, much bigger, and Adam with his loop model even much further, right? So this is, and they're much more precise than we are. The big advantage we have here is that is of symmetries, right? This model has the JQ and the loop models have a Z4 symmetry, and the claim is that the Z4 symmetry gives ways to a U1 symmetry at the critical point. But that means that quadruple monopoles are allowed right? And that the claim is that these quadruple monopoles are irrelevant at the critical point. We have skyrmion conservation because the skyrmion has a charge, the skyrmion is conserved. That means that we have a monopole-free realization of the DQCP. Did we win anything out of this? I'm not sure, but it's at least a different realization of what we believe to be the case. And then all the questions about, weakly first order or not weakly first order, we have no possibility to cope with that. Right? Our system size are just way too small. So that I think cannot. I don't want to go there because we can't say.
A question.
Yes, please.
I thought at some point you emphasized that your physics is happening at sort of finite chemical potential, and so particle hole symmetry is broken.
Yes, I did.
Is that the case of the other models you're comparing to right now?
No. So there are 2 axes to this plot. Here it is, right? There is an axis which is lambda here.
Yeah.
The particle hole symmetry is always present.
Right.
Right. And this is the axis where I can connect to the DQCP of Anders.
Good. Okay, I see.
And then there's another axis which is different than what I don't believe that, I don't know how you can do this in the JQ model, right? this axis of doping, right?
Right.
Which is really new, right? This
Okay.
has no there's no counterpart which was Assad, and there I believe the particle symmetry is broken, and it's most probably not a Z equals 1 transition. That's what
I see. Very good. Sorry, I think I got confused. I thought you were talking about that transition all this
we
time.
have two. It's like you know, when you come from the solid state, you have a mod insulator, and you have two ways of going out of the mod insulator. Or you stay at half filling, and you look at the bandwidth. So this is what we call bandwidth control transitions, and then you can dope, right? And these are doping induced transitions, right? And
Very
they're different things, or in hardcore bosons also.
Very, very good. Okay, thank you. Sorry.
Excuse me. At some point, you actually had a full SO5 symmetry.
Yes.
And broke it explicitly, right?
It's broken explicitly by this term, right? And the model has an SO5, SO3 times U1 symmetry. Right?
You remove that breaking.
I
You
can't.
simulate.
So that's the next part of the talk,
Okay.
right? That's the next part of the talk, right? Thank you. Okay, so the next part of the talk is, can we define a model that removes this SO3 times U1 breaking? It really has an SO5, right? And so what we would like to simulate is essentially a discretized a regularization of this model, correct? That was your question, right? And that is actually that's hard, but we somehow so the idea really comes from Michael Salato, and then the very hard work was done by Senju. What he did was remarkable. So Senju was a PhD in Würzburg, and now he's a postdoc in Dresden at the NPI PKS. And so what is so that's what we would like to simulate for exactly the same, you know, where now I don't have a theorem for this, but I cannot write down a lattice model which has the SO5 symmetry. And if you can, tell me, right? I just don't know how to do it. And so we had to go and look at different type of regularization. And the idea here is to use a Landau level type regularization for this continuum field theory. Okay, so that's our goal. You know, simulate this, and the only parameter we will have is G, right? Right. We just vary the difference. Okay, so here's how we do it, and let me hope that I get this correct in the time I have. So we start with Landau levels, right? We're going to work in continuum Landau levels but just to place everything in you know, give you a nice picture. Essentially, let's consider this Hofstadter butterfly on the honeycomb lattice, and this is basically our half-field Landau level, which is this object. And this one has an SU4 symmetry. Basically, it has a fourfold degeneracy, right? And the number of states which are here are given by the flux, by a number of flux points. Right? So if we work in a Landau gauge, right? So that ky is a good quantum number, okay, in one direction, and ky goes from 1 to n5, which is the number of flux quantum going through my whole lattice, right? If you want. And this here, this C dagger of ky n alpha, this generates an electron, so an electron, canonical electron creation operator, ky, basically momentum. The Landau level index, n equals 0 will be this index here. So I'll just put n equals 0 alpha, right? And this is the wave function of the 0th Landau level. Now, so this object, because I'm not summing over all the n's, I just take n equals 0 here, basically, right? This gives me my psi, and this is the projection of the field operator projected onto the 0th Landau level. Okay. Of course, this does not have any canonical commutation relating to very complicated object systems. So we will work with this, right, on this Landau level, and define this Hamiltonian on this Landau level. Now, because the Landau level this has a fourfold degeneracy, right? I can define 5 mass terms. So tau z sigma, tau x, and tau y, right? These are all anti-commuting mass terms. So this is the SU4 term, right? Doesn't break any symmetry. This would be, let's say, the spin, right? U of m for the spin, and minus UK, right, for the Kekulé, or basically VDS mass term. Okay. So now, so if I have those 5 mass terms, I can generate this MAD, which are the commutators of MA and MB, and I have essentially 10 of them, and these 10 matrices are basically the 10 generators of SO5. And when essentially when you put UK equals UM, we are the same, then this Hamiltonian here has an exact SO5 symmetry, and we can actually simulate it. Right? Okay, so that's the construction. Now, how does this relate to what we really want to do? Well, then you have to pick up a paper of Lee and Sashta of Subia, and if you put yourself at UK and UK, it's essentially the same thing as Avanov-Wiegmann, but then for a Landau level, you have the Landau level wave functions. Essentially, you can integrate out the fermion, and sure enough, what you will get is your desired model, namely, the Gaussian term and the topological Vesuvian-Witten term. Okay, so that's what we will put in the computer, right? There's just everything's projected onto a Landau level. We will use always UM is equal to UK to always stay explicitly at the SO5 symmetric point. And that's the construction we'll do. Now, it turns out, I won't go into details, but this is something you can show because of these papers I showed you before at the beginning of the talk about this symmetry understanding of what is sign free and what is sign full. And for this, you really have to go into these papers and look at it. And essentially, you can show that if your U0, so U0 is the magnitude of the SO4 symmetric coupling, this one here. If your U0 is bigger than -1, right, then you are sign free. Okay, that's the result, and you can look up this paper. It's very well shown. So in this paper, and also the one with Michael Salat. So just a comment. These are hard things to simulate, right? We're going to work in momentum space. When you work in momentum space, the interaction, which was contact in real space, becomes long range, right? When I work with a long range interaction, I lose a power of the volume, right? So that's already one power of the volume which is lost. Then, so you see, before I had a volume to the cube times beta. Now, turns out that I get, for this simulation, we need a volume to the 5 times beta. So one power of the volume is lost because we work in K space. So we go from 3 to 4, right? And then you suddenly realize that once you do Trotter decompositions, when you do Trotter decompositions of local operators, that's fine. But now you do Trotter decompositions of operators which are not local anymore, right? And so the Trotter error blows up as the volume. So to be sure that the Trotter error does not blow up, you completely go off bounds, then you have to scale delta tau, essentially. So this is a bit technical, but just delta tau as basically 1 over the volume. And that gives you the power the next power which you have. So these simulations are hard. They're v to the 5 times beta, but they're still a polynomial. Okay, so that's what's for the technical part. And now let me go and talk about the results, and then I'll stop. So for this half-filled Landau level, we calculate, to be sure that it's an insulator, we calculate the charge susceptibility, and sure enough, you have, for our biggest systems, here it converges. You have something which as a function of temperature, right, goes to 0 exponentially. So we have an insulating state. Good. So now the question is, what happens to this SO5 to the ordering? Is it an ordered state? Is it a critical state? Is it a disordered state? So what we compute is this SO5 correlation function, right? And we again, so this is defined like that. This is a 5-component object, and then what we calculate is then the correlation ratio. And so let me go back one step. The volume essentially, we sort of think about the magnetic field is constant, right? And we make the volume bigger and bigger. That means that the volume is like the number of flux quanta, right? So this has to be like 1 over the volume, right? So this becomes big system size, small system size. This is the correlation function as a function of U. So U is something like the stiffness, right? So when U is very big, then you see that the correlation ratio goes like this and then starts picking up. This is 100 flux quantum. We can't go beyond. I mean, our computer time was up, right? So this goes up here. So we claim that we have an ordered phase. But then what's very interesting is that when you go to lower values of U, up to U equals -1, then you have the impression that this correlation ratio, I don't know how to continue it, but one possible way would be to continue to something here which is finite. If it's finite, that means that I have a critical phase, right? That's the point. So now let's look at this correlation ratio as a function of U0. and you see, forget the smallest thing here, and you see that you do have a crossing, right? You do have a crossing. So this would be the ordered phase, and this is something, is it disordered, or is it something which goes to disorder? That means that would have to go to 0. So the scale is rather small, right? Don't forget this scale, this should go to 0. This maybe goes to something finite, and then we're done, right? We don't really know what to do. So this is the result, and now we're left with the interpretation of the result. And so the first thing is, what can we say for sure? Well, for sure, this is numerical, so there's nothing with some type of certainty. I think we're pretty clear that there's an ordered phase because this goes up like this, right? And then the second thing we can say is that at small u0, the correlation length rapidly exceeds our system size. That's essentially all I can say for the moment, and we are on these 10 by 10 type lattices and 100 foot square. Good. So what is the interpretation? Now, I guess that the interpretation of this is fun to do in an enhanced phase diagram where we have this line, which is the SO5 symmetric line, right? And then we put up here a symmetry breaking field, which breaks the SO5 symmetry towards a U1 phase or towards an SO3 phase, right? And let's start and play games. Let's assume that we always have an ordered state. Let's assume that this SO5 theory is always ordered. Then I basically have this phase, this ordered, it's a symmetry broken phase. And then if I want to go from the VBS to AFM, right, then it will be a type of spin flop type transition, first order type spin flop transition. Now, what we also have here, which is very consistent with the data, is we have this SO5 phase, but we have an SO5 CFT, right? Because this is somehow critical. As you would have, if you take the same model in 1+1 dimension, that would be an SO4. The SO4 is an SO4 CFT. It's basically the Heisenberg model, right? So this would be the pendant dimension higher basically than the SO4 1+1 dimensional CFT. So this would be a critical. This would be a SO5 CFT, and then we would have a critical point. So this critical point is essentially this crossing, which I was showing you here. That would be the critical point as a function of u. But we never get disordered, and we always keep critical. Now, if you think about this in terms again of this axis here, which reduces the SO5 symmetry from SO5 to SO3 times U1, then you have the very interesting possibility that, well, I mean, this is the critical point, which is an SO5 CFT, and then you break it, you go to VBS, you break the symmetry, you go to an AFM. That would be the scenario if you want to DQCP with emergent SO5 symmetry. Right? That's certainly what a lot of the numerics seems to show on an intermediate, at least on an intermediate length scale, on a very big length scale. Right? That we know that, right? The loop model for that. And then we have another possibility, which I think would be maybe even more interesting, and that is that we have a disordered phase, right? But then you would have to understand how to get a disordered phase without symmetry breaking of Dirac systems, right? And this disordered phase could be very interesting. So we don't have any evidence for this, but that could also be a possibility. And in that case, that means that there's an intermediate, when I go from the VBS to the AFM, around like this, basically I go through two phase transitions, an intermediate phase and another phase transition. One will be an SO2 CFT, one will be an SO3 CFT. Okay, if you talk to Adam about this, right? So I talked to Adam about this. Adam will tell you, well, most probably what happens, I mean, that would be another interpretation, is that these 2 points, basically, they collide, they meet, they collide, they go into the complex plane, right? And essentially, what we see is something which is maybe like this, but with a very, very slow scale, right? That would be one further interpretation that, okay, we see this at intermediate length scales, right? But this is maybe what happens because of the system. Okay, so I'm done for this part of the talk, and I think I'm fine to stop here. I mean, we would have 10 minutes for discussions. I'm fine to talk quickly about the last part, as you like it.
Could I ask you a couple of questions?
With pleasure, yeah.
One thing that I did not understand is, you were mentioning Wigman and Abanov's papers, and there, I mean, you get the West-Witten terms, which
Right.
clearly have sign problems, and I didn't understand how you evaded this.
Well, I can simulate a one-dimensional Heisenberg model.
Mhm.
The field theory has a topological term.
That's right. But
Same thing. It's a same thing which was touched upon by Uwe yesterday also, right? It's very formulation dependent, right? So that's yeah.
Absolutely. But then, what was the? So you somehow reduced those kind of models to not having these n fields, these vector fields at all, or you
No.
integrate them out somehow. Or
We really do. No, we really simulate this. What goes in the computer are the fermions, right? This is really what we simulate.
And how do you connect it to the West-Witten? I mean,
Well, you have an SO5. So how do I connect it? I essentially I connect it with this paper, right? I say that what I observe is a gap state of this, right? I mean, I put this in the computer. I put this in the computer, and I can do the simulation without a sign problem. Okay, so that's we should still talk about this. But then what I obtain is a gap phase. So what I showed you here is the charge susceptibility is going exponentially to 0. So it's a gap phase. There are no fermions. Okay. So if I have this, then I can go back to this model and then integrate out the fermion that you want. And what we get is essentially, if you follow the words of Subia, then what you will get is the Western version.
so yeah, okay. So you kind of do all.
Yeah. So I put in the symmetries, right? I mean, I know exactly that it's the same. You know, the symmetries work. That's what I do.
You could probably, the West-Witten term has a particular 't Hooft anomaly, and probably equivalently you could look at the 't Hooft anomalies of
Okay.
the fermionic model. That would be another way of showing that they're, you know. Okay, that's one question. The second question I had was, can you measure the, so are you sure, so you're convinced from your simulations that and all the symmetry breaking to SO3 cross U1 is relevant? Is that clear?
No, we didn't do that calculation. We don't know that. This is completely interpreted.
Mm-hmm.
This is a complete interpretation. We stuck the calculations were, we only did the calculations at the SO5 symmetric point. That's the only contribution we have.
I know, but you could look at the correlation.
Yeah, we could certainly look at we could certainly break this and see the relevance, right? That's certainly something we could, has not been.
Right, because there were these bootstrap works which claiming that people thought that maybe the VBS to AFM transition was had an SO5 enhancement,
yeah.
right?
Right.
And there was something inconsistent in the bootstrap.
So the story is the following: is that if you assume that you have an SO5 emergent symmetry, then you have a bound on the eta exponents, right? And the eta exponents have to be 0.52 or higher, and we have, and both Anders and get 0.25, something like that, right? So there's,
at least the early works of Bootstrap, they were all assuming what your symmetry is U1, but they were all assuming that they were symmetry breaking operators in the Lagrangian, like
yeah. So I think the Bootstrap, if I remember well, the emergence of the U1 symmetry is okay with the Bootstrap, right?
Yes.
From Z4 to U1, that's not a problem. There were two issues. There was if you have a critical point, that means only one relevant operator, then there is a bound on the correlation length exponent.
That's right.
And the bound on the correlation length exponent was what Anders has is dangerously close to this bound. That was one comment, right? So that's subject of discussion. But then so let's forget about this bound for the moment. But then there was another problem for the SO5. For the SO5 to be an emergent symmetry, you had to have an eta which was bigger than 0.52. I remember that. And what Anders and Adam have is 0.25, right? But it's very far. So that's really inconsistent. So the idea that you have SO5 emergent symmetry is maybe not correct. But you look at the data, right? I mean, you know these paper of the loop models of Adam, and they're just remarkable, right? I mean, it's if you did not have the conformal bootstrap, you would believe it, right?
Mhm.
Right. So I think this is maybe the reason why.
You could check all of
But
these.
sorry.
You could check all of this, but that would be very, yeah, you could check all of this, but
There is, I mean, your model certainly has SO5 symmetry, and all constraints of bootstrap should be satisfied here.
right.
Also, I noticed your correlation lines exponent is like bigger than Anders' result, right? You have like 1.7 something.
Yeah. So but we have error bars, right?
Okay. Yeah.
We have error bars, right? So that's the problem of working with the fermions, right? So
Mhm.
it is bigger, but we have error bars. But strictly speaking, we should be careful, right? I mean, it's not a big difference if you take the error bars.
Yes, yeah.
Yeah, good point. I agree.
By the way, one comment is that I've been working on some models where we can formulate a fully bosonic model with U1 cross SO3 symmetry.
Yes. Yeah.
Fermions. I was wondering whether you think it would be worth doing.
If you go to, is it simple to sim? Is it a simple sim? Is it a?
It's relatively simple to simulate. It's nothing too fancy. They're field theory models, but they have the same
Okay.
Transitions and everything. I don't think I could do SO5. At least I don't have an idea how to do that. But for U1 cross SO3, we can impose an exact topological symmetry, eliminate monopoles.
Yeah. So you should. So the question you think, I have nothing to say about that. If I think it's worth it or not, that's your decision. I think you have to ask your question: is the Z4 to U1 symmetry is sort of accepted, right? That's not the issue. I have the impression. But any model which, if you can do, I think that if you have to go to if you can go to big lattices, then it's worth trying, right? That would be my take.
The catch here is whether I can go to big lattices. I'm sure somebody can go to big lattices.
And then you have to find a collaborator, right? Yeah. Hibu is coming this afternoon, right?
Yes.
We should talk to Hibu once he's woken up. Okay, so I think I'll conclude because the time is up. I just wanted to conclude these are my conclusions. I didn't talk about the new stuff we were doing, and so I'll quickly tell you. So these are my summaries. Just give me 5 minutes for the summaries. For Monte Carlo, you can do a lot of things. I hope I've convinced you. This is what we talked about, the Skyrmont superconductivity. Then we will go to this phase, this nonlinear sigma model, this explicit SO5 symmetry where we can do some calculations. And this is what I did not talk to you about. This is a new model which is pretty fun, which we don't really understand. It's a model where this is the model, and it's basically a model where if you start with 12 two-component Dirac cones here as a function of J, right? You will only partially gap out the Dirac cones, and that's because you have an SO3 mass term, right? And if you look at the SO3, always has, if you look at the eigenvalues of SO3, there's always 1, 0 in SO3, right? Right. So that's basically the idea. So essentially, you will gap out. You have an SO3 semi-metal, right? So this is a Grosvenor SO3, a semi-metal where you gap out only 8 out of 12 cones, and 4 remain metallic, right? And then again, this model again has another transition, which is going from a semi-metal with an SO3 broken symmetry to a U1 insulator. So the U1 symmetry is basically related to this tau, right? So this sigma has 3 components. This lambda is like a layer, has 2 components. And this is basically interlayer coherence, right? Tau x, that's a broken U1 symmetry. And that is a U1 insulator. Remarkably, this seems to be continuous, right? So, well, look at the paper. The paper is just online. This seems to be continuous. So we have no idea of how to understand this, because if you do a mean field transition for this, you have an extremely strong first order transition, right? So you can look in the paper. The other thing which is happening here is that the exponents we get from the numerics for this sort of Grosneve SO3 transition are actually pretty different from the exponents which have been calculated with epsilon expansion, large N, and FRG, right? So it seems to be, a sort of something, at least for me, new in the sense that you get a metal-to-metal transition where you only have a partial gapping of the Dirac cones, where the exponents here are, maybe we have to go to bigger system sizes, all this, but for the moment, there's a big discrepancy between what the Monte Carlo says and the field theories. The field theory has no topology again, right? There could be some topological effects of the SO3 order parameter, which are not taken into account. Certainly here, if you do mean field, with no topology of the order parameter, then you get a very strong first order transition between here and here. The numerics show something which is again weakly first order, right? So it's published here. It's on the archive, right? So this is a work from the Zihong Liu et al. So that's with Matthias Wojta and Lukas Janssen and myself, and that's on the archive this month, right? If you're interested. And with this, I will stop because I'm on time. So thank you very much.
There were many questions during the talk. So I'm wondering, do people have questions who haven't asked any yet? I'd like to hear from the other people in the audience. Possibly not. I had one question, which I'll ask only as a chair. I feel I shouldn't be giving myself privileges, but since okay, I'm going to take them. Could you say a few words about this intriguing finite doping transition, which I think you said is something you don't know anything about, that there's no field theory description for it yet. Is that correct?
Yes, that's what I say. So what do you want me to say about it?
There's no, you cannot, for example, break particle hole symmetry in some of the existing deconfined critical points and try to understand it in that manner, or is that too difficult?
The breaking of particle symmetry is a big symmetry. You basically break the whole conformal invariance, right? I mean, right.
It's
a big thing, right?
Yeah.
Listen, I'm maybe not the correct person to talk about this. Chong Guang is on the paper, right? So you should talk to Chong. Maybe you know him.
No, but
it does not seem to be an easy. It's open, right? That's all I can tell you, right?
Okay. Okay.
I just don't know how to do it. Chong neither, right? I don't know. But I just don't. I can't write down anything which is. Doping is hard. Doping is hard because you suddenly have break all the symmetries you like, right? Mm-hmm. Well, Lorentz symmetry is very nice to have, right? Right.
So you'll obtain some z not equal to 1 critical point, is your guess?
My guess is it is. I think my guess it will be this. It will be something maybe, yeah. So we believe that it's Z2 or bigger.
Okay. Do you have a number for Z?
2 or bigger.
2 or bigger. Okay.
That's the claim.
That's the claim.
First order transition or 2 or bigger. That's what we can get out of it.
Okay.
Right? Because we can monitor the chemical potential as a function of doping, and from that we can get
Thank you. Any other questions? Okay, so if not, we will reconvene at 2:15 this afternoon with a discussion session for Fakher, so people can share their questions, can think of if there are more questions then. And until then, that closes the morning session. See you all at 2:15.
Bye.
Actually, Tin, do you have a minute?
Well, should I stop the live stream?
Oh, maybe, yeah, sorry.